Hey, good afternoon, everyone. Welcome to today's webinar. My name is Huaxia Rui. I'm a faculty at Simon Business School of University of Rochester. So today I'm going to talk about the rise of AI and the future of jobs. Obviously, this is a very big topic. A few years or maybe even a few months from now, I will be surprised by my views myself. So I try not to make any bold prediction. So let's get started. So before I talk about this topic, I want to first clarify a few common misconceptions, or to talk about some related concept. The first one is the difference between intelligence and consciousness. Now, these are two very different things. From scientific point of view, intelligence is something we now have a good definition, but for consciousness, we don't. And a lot of the hype about the threat of AI taking over the world, AI become autonomous, this is related to the consciousness part. We do not touch on that. Whether consciousness even exists is still an open question. Now, the second clarification is about the difference between AI and AGI. I guess many people now are very familiar with the concept of AI. A lot of you are probably also familiar with the idea of AGI, or artificial general intelligence. So that concept is certainly popular now with the OpenAI. Their stated mission is to ensure that AGI benefits all of humanity. And also in their charter, they commit to stop competing with and start assisting any other project on AGI if they're getting closer. So AI is basically the current technology, but AGI, depending on who you talk to, is probably still years, decades away from now. The analogy I would like to draw from about AI versus AGI is back to 1950s when Alan Turing wrote that famous paper about the universal machine. So that concept is revolutionary. In a sense, it's kind of like saying, well, look, we don't have to build different machines. We just have to have one universal machine, and then we can use program to achieve different kind of functionality. Now, if you think about AGI, it's kind of similar in that idea. Right now we have an AI for this and an AI for that, but maybe in the future we will have only just one AI that can learn everything. So, but we are not going to touch on AGI. The third concept is the kind of AI. So here I try to distinguish what I call statistical AI versus causal AI. Now, most likely you have never heard about this term, statistical AI. Well, popularly it's just known as machine learning. So, but because this approach has been so successful, now we just talk about machine learning, or we just use AI to refer to statistical AI. However, there is some big difference between statistical AI and causal AI. Now, if you recognize this guy, his name is Aristotle. So basically more than 2,000 years ago, he's been talking about two approaches of gaining knowledge. One approach is induction. The other approach is deduction. So the deduction is like, when you use logic, when you prove something in mathematics, for example, you have step-by-step process. Or when you think about detector, you have step-by-step process where you use logic and based on some premise to draw some conclusion. Induction is completely different types of understanding or gaining knowledge. We try to use data and we try to generalize. So this distinction is very important. And my claim is that the current statistical AI approach is still far from good reasoning, meaning it's good at deduction. It's getting better and better with induction, but for the deduction, it's still probably years away from now. This morning I actually tried the latest version of ChatGPT just to illustrate well, just to see if they have made any progress with respect to the its deduction power. And I don't know if you can see this clear enough. I basically ask 3 questions. The first question here is a probability question, and it gets the wrong answer. Well, it gets the wrong answer for all these questions. But if you look at how they get wrong, here, I don't know if you can see it clearly, but let me just read it for you. Since there are 15 balls, 7 are odd numbered. 1, 3, 5, 7, 9, 11, 13, 15. So there are 8 numbers, not 7. So even though it can appear to be reasoning, it is not. And the second, the one in the middle, is another probability question. Actually, both questions from my course. So here you can also see the mistake it made is at the second step. Now, the last one is not a math question. Rather, if you look at this one, I'm just saying, okay, people are walking on the lake, probably in Rochester in the winter. What should I wear? So ChatGPT would recommend wearing some lightweight, breathable clothing. So you can see that these ChatGPT as an example of the most advanced AI tool right now. You can see that it can spit out answers. It can give you a long essay, but it's not based on the reasoning. So that's why here the framework, we try to distinguish between this statistical and this causal approach. Now, this is something I also want to show you before I talk about my framework. Here, this is actually from a paper published 20 years ago. And 20 years ago, it's not such a long time ago, the idea of AI is really that AI is good at routine tasks, not good at non-routine tasks. And how do they define routine versus non-routine? Well, for routine, it's by following explicit programmed rules. While for non-routine, these are the kind of tasks that you cannot specify the rule in a very explicit way. And of course, if you look at the table where they showed example, you can see it doesn't apply nowadays. For example, medical diagnosis, legal writing, all these things can now be performed by AI. Yet in the past, it's considered as non-routine. And similarly, like truck driving, these kind of tasks can be done by AI. So the reason why in 20 years ago, people think that in that way, they think about this routine versus non-routine dichotomy is really because at the time, the statistical AI is not as well known in economics, in business schools at the time. So all those, this dichotomy between routine versus non-routine is really about this causal versus statistical approaches to AI. So I try to give people some tool, some visual tool to understand what AI can achieve. So this is what I came up, what I call a lens. So if you look at this, we can think about any task that humans do in their job as a mapping or a function that takes some input and produce some desirable output, whatever that means. The desirable is whatever we human define. Or if you want to think about this more probabilistically, you can think of this as a distribution. So at the heart of any task is this concept or this idea of task learnability. And it can be further decomposed into statistical complexity and computational complexity. And because these two almost orthogonal components of a task learnability, we need 2 types of resource to learn. One is the statistical resource, basically data. The other one is computational resource, your computer, CPU, GPU, TPU, whatever. And you use some learning techniques to combine these resources to tackle this learnability problem. Now, most of us are familiar with this idea of statistical complexity. You definitely need data, but this idea of computational complexity is not so well known, at least among the people I've talked to. So here I'm showing you a simple example that illustrates that low statistical complexity does not imply low computational complexity. So if you look at these pictures, the one here and the one here, I don't know if you can see clearly here. These are from some movies where we try to capture, decode some secret message. So this is really about cryptography. So why do I talk about cryptography here? Because cryptography is the opposite of machine learning. So if we look at the one on the bottom, the image in the bottom, think about this example. Nowadays, most of those messages we exchange on the internet is encrypted through a public key infrastructure. So basically, you have a public key, that yellow key here. You encrypt your message. You share that encrypted message with your recipient, the intended recipient, and the recipient will use his private key, the blue one, to decrypt the message. Now, the key thing here is that this public key is known to everyone. So it's public. But that means, okay, if I know your public key, I can create a lot of pairs of clear text to encrypt message, or vice versa. Think about this. I have a lot of pairs of encrypted message and its corresponding clear text. So now the problem of figuring out your private key becomes a learning problem, a machine learning problem, basically. But we know this is practically infeasible. And here you can see clearly that the constraint is not about the data size. It's not about sample size. You can use a public key to generate as many data points as you want, yet you cannot learn it. So in computer science, of course, these concepts have been rigorously studied, and it turns out that the learnable, what is learnable, is a actually subset of what's called P, polynomial time algorithm. So this is just to illustrate the point that we can, when we think about the task learnability, whether a task can be learned depends on two things. Back to the this lens, you have two orthogonal dimensions of task learnability. So now we can represent so conceptually we can represent every task as a point on this task plane. And then we can think about at any time, you have an intelligence level of the AI for that particular task. So if you plot all those tasks that we ever care about in our economy, then you have an intelligence service. So I call this the CIS, the current intelligence service. So you can think of the technology advancement as the uplifting of this surface. So how can this move up? Well, one approach is to have more data. The famous example is this ImageNet, this data set with more than 14 millions of image of more than 20 categories. So these annotated image allow computer scientists to learn, to improve their vision algorithm to do image classification, image segmentation, etc. So if we keep that framework in mind, this is obvious, right? You have more data because now you have more statistical resource. But of course, depending on the task we're looking at, you benefit differently. If you have a task that's very high in your statistical complexity, but low in computational complexity, then you will gain the most from training instances. Now, the second mechanism to lift this intelligence surface up is through faster computation. And almost symmetrically here, you can see that if we have, for those tasks that are very low in statistical complexity, but high in computational complexity, you will benefit the most from faster computation. The third mechanism is that triangle in the middle of my diagram. When you have innovation in learning techniques, there are two types of learning innovations. One is with the so-called beta hypothesis class. Examples are AlexNet in 2012, the Transformer in 2017. Of course, now, Transformer actually that's the framework behind the GPT. And you can also have better algorithm. Examples include regularization techniques. So these three mechanisms leads to improvement in AI performance. Now, how do we relate that to jobs? So you can think of this. First, you can think of another surface, which I used some gray, this gray color, this flat surface, to indicate what we call a minimum intelligence surface. Basically, the level of performance for AI to be usable in a practical sense. So a job, we can think of a job as a set of tasks. You know, every job involves different kind of tasks. For example, if you have think about the job of a professor, you have to teach, you have to do research, and sometimes you have to entertain your alum. So you have a lot of tasks in each job. So here we use those little dots to indicate task, and the circle indicate a job. So if you have a job like this, the one to the left, that green one, so for every task in that job, the intelligence surface is already above it, above the minimum intelligence surface. So that kind of job is called in the substitution phase. If you, on the other hand, you have that job on the right, to the rightmost, it's all in red. That's what we call a decoupled phase, because the minimum intelligence level is not reached for any task in that set. The interesting part is this honeymoon phase, when you have part of those tasks in a job that can be completed satisfactorily by AI, but some other tasks that cannot. So this is what I call a honeymoon phase. So what's the implication of that? Well, you can become more productive. Okay, but of course, in real life, you don't have just one single intelligence surface. Depending on the organization, depending on region, you may have different surface. So here we plot 3 to illustrate that you have some AI novice employers, and you have some very proficient employers. So even for the same task, for some, it's in the honeymoon period. For others, it could be in the decoupled, or it can be in a substitution. So we should really think about each job type as a probability distribution over the 3 phases, reflecting the different proportion of organizations for whom the job types are in each phase. Okay, so this is basically the conceptual framework to think about the power of AI and how it relates to job. Now, more practically, we built an economic model to understand further how this dynamics work, and we derived a result which I call inflection point conjecture. So basically, we find that initially, we find this inflection point before AI crossed that inflection point. Whenever there's improvement in technology, human workers will produce more services. They will earn more. However, once you pass the inflection point, AI improvement will make the human worker worse off. They will produce less and earn less. So we test this hypothesis we test this conjecture using 2 hypotheses. We look at translation and we look at web development. And we use the launch of ChatGPT last year as the shock. Basically, when you after launch, you have improvement. So where that improvement leads to better pay, better job, more jobs, or will it lead to less pay and less job? So we look at these 2 groups of 2 types of job, translation and web development. And we find that for translation, indeed, there is a decrease in the number of jobs, and there's a decrease in the number of earnings. For web development, we find the opposite. So these evidence indicate that for translation, the inflection point probably has been crossed, but for web development, not yet. Now, I have to certainly mention about the last question, which is probably in the mind of everyone who think about this AI age. What kind of jobs are safe for statistical AI? So I summarize this in this picture, or this is really SEAC. So this goes back to this framework that I propose here. So surprise, any job that requires unexpected thinking would be hard to be replaced. Why? Because if it's unexpected, you will have less data point. So the statistical resource would be deficient. The second type is what I call this emotion. Anything that involves detection and reaction to human emotion and human psychology, or what I call natively human jobs, they will be hard for AI to do well. And the reason is really about the computational resource. Now you might be surprised how come these kind of jobs are tasks are difficult to compute. Well, we have to keep in mind that our learning does not start from the day we were born. It starts probably tens or hundreds of million years ago in the evolutionary process. Kids or small babies, they are good at learning a lot of things that are difficult for a machine to learn. And the reason is really, I think, that in our biological hardware, we inherit a lot of the traits from the evolution. And of course, the last type, which is always important, is this the kind of job that requires the development and maintenance of AI. You need someone to manage that. Okay, I guess I'm run out of time, 2 minutes over. So I will stop the presentation and open the floor for questions. Okay, so I'm going to start with one of the question that that was raised to me earlier. The question, let me read the question. How will AI affect educators or education business in general? So this is clearly related to our own profession. So the way I think about this is that learning or education, if you think about education as mainly about teaching and learning, it's actually more complicated than just giving a list of facts or a map of knowledge, because concepts, they are organized in a very complicated hierarchy. And if you haven't understood certain concept, it will be difficult to understand the next level of concept. So human educator play a very big role here in terms of detecting which concept is obtainable, is natural for a student to learn. My favorite example is about giving example. So oftentimes it's very hard to, based on my own experience, it's very hard to convey an idea to a student unless I can give a very good example. If you give a good example, oftentimes a counterexample that surprises someone, when you have that, the students suddenly get it. So this is really about this idea that concept, they are layered. There's a intricate hierarchy here. So the human educator, they can play a big role by deeply understanding the subject and also detecting what is the example that's needed to clear the concept to make the student understand the whole idea. Okay, let me so there's one live questions. Okay, So let me start with the first question. Let me read this question. There are many emotional models or sentiment analysis tools. So wouldn't they improve emotion handling jobs for AI in the future? Also, what if more females train AI models? Would this improve childcare business? So I think that will definitely improve the performance of AI. However, even the very concept, the detection, the classification of emotion is not universal. Emotion science is still, I think, still in the early stage. Being able to detect one's emotion, especially by through interaction, not just like the positive, negative, these two aspects, but richer, more complex emotion. That is something that I think humans can do really well, and the reason is really because we owe a lot of that ability to the evolution. And also detection is one thing. There's another aspect, that's the reaction. To what extent will the recipient feel that emotion has been well understood and and interaction is productive. Second question, do you have any estimate of what percentage of job will be affected by AI in the next 20 years? I don't. So that's a very difficult question to predict what's going to happen in 20 years. Let me put it this way: if AGI is possible, then there will be no job, basically. But I think AGI is unlikely to be realized in the next 20 years or so. So most likely AI will just have will affect one area, one type of job at a time. So this is really hard to predict which one will be the next. But I do think that based on the inflection point conjecture that I proposed, once you cross that inflection point, then there's going to be acceleration of substitution. Especially once you work side by side with AI, you are contributing a lot of more data points, which will make the AI performance even better. So in that sense, it's kind of ironic that while we benefit from that, we're also contributing to the eventual substitution. Another question is, how can users be confident of this technology when it seems to provide incorrect responses? So I guess you are referring to ChatGPT and the three examples I illustrated. I think this you have to put this in perspective. Think about the before ChatGPT, the state of art is way worse, much worse than ChatGPT. And even if you compare ChatGPT 3.5 and GPT-4, the improvement is also significant. So in that sense, I think it's very hard to predict what's the next step. Even though I personally believe that there's a fundamental difference between statistical AI and causal AI. But what if there's not? If that's the case, then that basically paved the way for AGI. So the next question is, oh, maybe I'll just answer one last question given the time. How do you see AI affecting future jobs like online translating? Will they be completely wiped out? Or do you think there will still be some amount of human labor doing this job despite the powerful development of AI? I think for online translation, I have a very pessimistic opinion. I think there's this kind of job is likely to be wiped out. It's just a matter of time. Okay, thank you thank you everyone for attending today's webinar. I'm sorry I can't answer every questions. So feel free to email me and I will be happy to discuss through that.